Hello class, we're going to be discussing today angular momentum quantum numbers, and in order to do that we need to first talk about boundary conditions. So the wave function for the rigid rotor can exist anywhere between angle phi and angle phi plus 2 pi. Remember, we're dealing with a circle and 2 pi radians is equal to 360 degrees. So phi of phi plus 2 pi is equal to rigid rotor wave function phi. We cannot distinguish a particle that has rotated n times versus n times plus 1 because that brings it back to the origin. So if we have a particle that has rotated a certain number of degrees and then we add 2 pi to that number of degrees, that brings us right back to where we started, and we can't tell the difference between those two. So in a circle, angles phi and phi plus 2 pi are indistinguishable. So let's see what that means for our rigid rotor wave function. So capital Phi of phi plus 2 pi is equal to our wave function in its exponential form, e raised to the I times m sub l times quantity phi plus 2 pi is also equal to e raised to the I times m sub l times phi, because phi plus 2 pi is indistinguishable from phi. So when that angle is equal to 2 pi, we can say that our wave function of 2 pi is equal to e raised to I, the power of I times m sub l times 2 pi. And using the Euler relation, we can expand that exponential form to the trigonometric form, setting it equal to cosine of m sub l times 2 pi plus I times sine of m sub l times 2 pi. So we know from our discussion of quantum numbers that m sub l can go from anywhere from negative L to positive L. So m sub l can have a number of integer values. So let's say that m sub l is equal to 0. Then our wave function at 2 pi, as defined previously, at angle 2 pi, our wave function at 2 pi is equal to cosine of 0 plus I times sine of 0, which ends up being 1 plus 1, which is equal to, 1 plus 0, which is equal to 1. If, however, our m sub l quantum number is equal to 1, we can say that our wave function at 2 pi is equal to cosine of 2 pi plus I times sine of 2 pi. And then our wave function of 2 pi is equal to 1 plus 0, also equal to 1. And then if we can plug in a last value, we can say that m sub l is equal to negative 1, our negative integer. We have the wave function at 2 pi is equal to cosine of negative 2 pi plus I times sine of negative 2 pi, which is again equal to 1. So this allows us to state, or to prove rather, something for ourselves, which is that for any wave function at angle phi, the values for m sub l have to be integers. They can be 0, positive or negative 1, positive or negative 2, positive or negative 3, and so forth. And the reason for that in terms of a wave being a standing wave in a circle can be shown with these images over here. So in image A, we have m sub l as a positive or negative integer, where we have our wave function about a circle, and that is a nice standing wave that begins and ends with itself, and it's just standing there being a standing wave. If m sub l is not a positive or negative integer, we get a whole mess of constructive and destructive interference, and we do not get a standing wave. So this brings it back to our standing waves being allowing for quantized energy, just like we've seen in the simple harmonic oscillator and in the particle in a box models. So let's now bring this back and extrapolate and show that this brings us to a boundary condition. So for any value of wave function based on phi, our m sub l values have to be a positive or negative integer. And as we saw up here, this always results in the wave function being equal to 1. So we have the boundary condition that wave function of phi is equal to e raised to the power of I times m sub l times phi, bringing it back to the exponential form using the Euler relation, and showing that this is going to be equal to 1 provided that m sub l is a positive or negative integer. So now, does this boundary condition make sense for normalization? So let's bring in the normalization equation, showing that we have the normalization constant squared outside the integral times the integral from the limits 0 to 2 pi of the complex conjugate of the rigid rotor wave function times the normal rigid rotor wave function, d of phi, is equal to 1, where our wave function is equal to e raised to the I times m sub l times phi. Now the complex conjugate of this is itself just with the exponent being negative, given that there's an imaginary component. So now we have a squared times the integral of e raised to the negative I times m sub l times phi times e raised to the positive I times m sub l times phi. All of that is integrated from 0 to 2 pi and set equal to 1. If m sub l, for example, is equal to 1 and our angle phi is equal to 2 pi, we know from earlier work that our normalization constant a is equal to the square root of 1 over 2 pi. We can solve and find that the square root of 1 over 2 pi times the integral of these wave functions multiplied together is just going to be equal to 1 over 2 pi times 2 pi being equal to 1. And if you review your notes, you can find that when you multiply these wave functions together, the exponents add to one another and cancel, and we get in the integral e raised to the power of 0, which is 1, and then when we integrate from 0 to 2 pi, this whole expression here just simplifies down to 2 pi. So now, as we build towards discussing other quantum numbers, let's review some that you may have seen before in general chemistry. So our quantum numbers that we've identified so far have been our principal quantum number, which is given the symbol n. And the principal quantum number has possible values that are any positive integer, so 1, 2, 3, 4, etc. We have the angular momentum quantum number, which gets the symbol L. And L can be any integer, 0 or greater than 0, 0, 1, 2, 3, etc., with its maximum possible value being 1 less than the principal quantum number of a given set. And the angular momentum quantum number symbol L is describing the shape of the orbital, and so when we get values like 0, 1, 2, or 3, we ascribe them letters like s orbitals, p orbitals, d orbitals, and f orbitals, and that is all based on its angular momentum quantum number L. A subset of that is the magnetic quantum number m sub L. And this has possible values of any integer that ranges from negative L all the way up to positive L, including things like negative 1, 0, positive 1, etc. And then we have the spin quantum number m sub s, which is either equal to a positive 1/2 or a negative 1/2. Now let's discuss the angular momentum quantum number in terms of vectors. So we have angular momentum vector L, with a half arrow above, is perpendicular to the plane of rotation, and this follows the right-hand rule. So if we have a rigid rotor rotating viewed from above counterclockwise, and we have rotation in this direction, our angular momentum vector is going to be going straight up, and that follows the right-hand rule. The angular momentum of this system also precesses about a direction. And what this means is that it takes up a certain volume and moves sort of like a top. So rather than just have the vector going vertically in space and just sort of rotating like this pen, what it actually does is it takes up a certain amount of volume by going in one direction and then rotating like a top, like this. And that precesses and contains a certain volume, and that volume is always in the shape of a cone. So the angular momentum vector L arrow is seen precessing about in a certain direction in space in the shape of a cone. And L is equal to the square root of angular momentum quantum number L times the quantity L plus 1, and that whole quantity is multiplied by h bar, where again, lowercase l is the angular momentum quantum number. So let's look at an example where that quantum number is set equal to 2. That would result in the magnitude of our angular momentum vector being equal to the square root of L times quantity L plus 1, all multiplied by h bar, which would be equal to the square root of 2 times the quantity 2 plus 1 times h bar, which is equal to the square root of 6 times h bar, which is equal to 2.449 h bar. So what is this value? This means that at L is equal to 2, and L being equal to 2 would be a d orbital. So in something like a d orbital, we would have the magnitude of our angular momentum vector being equal to the quantity 2.449 h bar. So what the heck does that mean? That has to do with the magnetic quantum number. So at a given angular momentum quantum number L, there are only certain possible m sub L values. And different m sub L values have a different effect on orienting the angular momentum vector L in space. And here we see a diagram shown below, where if we're starting at the origin here, we can have our angular vector, this red line, pointing in certain directions. Now, as we just calculated, for something like L is equal to 2, our vector has the magnitude 2.449 h bar. So in this system, in this example, this is held constant. And that's why these red lines are all the same length. So they have the same magnitude, but they are operating in different directions. The direction of the vector is controlled by m sub L. So being the most vertical, this is when we have an m sub L value that's equal to 2. When it's a little bit less vertical, we have an m sub L value that's equal to 1. And when it's horizontal, it's equal to 0. And when slightly horizontal but negative, it's -1. And vertically but negative is -2. So the m sub L value being equal to its value times h bar orients the vector in space. And only certain orientations are possible, and this results in something special, which is spatial quantization. So the orbital, as described by the angular momentum quantum number, can only exist in certain orientations. And these m sub L values result with, or in coordination with the vector, result in things like dz squared orbitals, dxy squared minus x squared minus y squared orbitals, dxy orbitals, things like that. So this is where the position in space comes from for the d orbitals. But what's important to us is the fact that we have these m sub L values orienting our angular momentum vector in space. And that brings us to our next quantum number, the spin quantum number. Spinning particles create a resultant spin angular momentum vector, s half arrow. The spin angular momentum vector s is perpendicular to the plane of rotation, follows the right-hand rule. This is just the same as our angular momentum vector. So if we have rotation from above counterclockwise, just as before, we would have our spin angular momentum vector going vertically here. So what is the point of bringing up our spin angular momentum? Turns out vectors L and S couple with one another. And that is called either commonly LS coupling or Russell-Saunders coupling. So our vectors for angular momentum and spin couple with one another, meaning that they sort of add to one another to create a total angular momentum quantum number J. So this is probably a quantum number that you haven't seen before. And this is simply equal to L plus S. And so if we were looking at how these vectors were additive to one another, L and S, if we had L kind of going in this direction and then S is going over to the left and vertical, the total vector is seen here from the origin out to the resultant location. So we have J. So J starts here and ends here. And so since L and S, our angular momentum and our spin vectors, couple with one another, we can always bring them together and describe the system using J, our total angular momentum. Now in this funky drawing over here on the right, you can see how these vectors are adding to one another, given that each one of them is also precessing, so looking sort of like a top. So in blue, you can see that the L angular momentum quantum vector is taking up this cone here, and it's vector has a direction going over here to the right, and then S sort of builds off of that, giving this green cone, and the sum total is J going in this direction, and it has its cone taking up this volume shown here. So, since LS coupling is inseparable, the J energy levels, it is J energy levels that appear within the vibrational energy levels mu. So inside the simple harmonic oscillator levels, nu 0, nu 1, we have our rigid rotor energy levels, but our rigid rotor energy levels is not just our angular momentum. We also have to incorporate spin, since those two are connected with one another. And so our energy levels are actually described by J states for rotational spectroscopy. So how does that look? If we have a certain energy well, shown here, where we have on the y-axis energy and on the x-axis internuclear distance, I've marked in blue where we would have our vibrational energy levels from the simple harmonic oscillator, nu double prime equals 0, nu prime is equal to 1. And within those, we have our rotational states, which are described by the total angular momentum quantum number J. So here we have J double prime in the ground state, energy level 0, energy level 1, 2, and 3, and in the excited state J prime equaling 0, 1, 2, and 3. So now that we've discussed our total angular momentum quantum number, we can rewrite our eigenvalue energy equation. So what we left off with last time was energy E based on our magnetic quantum number m sub l, is equal to h bar squared times m sub l squared divided by 2 mu r naught squared. Now, when it's based on the total angular momentum quantum number J, E sub j ends up being equal to h bar squared divided by 2 mu r naught squared. But instead of being multiplied by the square of the magnetic quantum number, instead, we're multiplying by the quantity J times J plus 1. Now we can simplify this whole expression using this substitution here, where we have h bar squared being equal to h squared over the quantity 2 pi squared, which is equal to h squared over 4 pi squared. So when we substitute that in for h bar, we get this expression for E sub j, which is equal to h squared over 4 pi squared times 2 mu r naught squared times the quantity j times j plus 1. And in the denominator, we can multiply the 4 and the 2 by one another to get 8, and we can substitute mu r squared for our symbol for moment of inertia. And that gives us equation 2 for the project that you're going to be working on for the rotational spectrum of HCl and DCl for project 2. And equation 2 for rotational spectroscopy of HCl is as follows. E sub j is equal to h squared over 8 pi squared times I, the moment of inertia, times the quantity j times j plus 1. And so what you're going to see for the lab is that within the simple harmonic oscillator, we have our vibrational states, and within those we have our J states increasing in energy above. And then there's a certain transition that happens from the ground state to the excited state, and then we are again in vibrational states. So it's a little tough to read, but this is nu is equal to 0, and this is nu is equal to 1. So this is our vibrational excited state. And shown here are some possible transitions between J states of the ground vibrational state to the excited vibrational state. And what that ends up giving us is going to be a spectrum, which are two sort of humps of peaks left and right. And so for a rotational spectrum of something like HCl, given all of these J states that we're now transitioning between, we get something that looks like this, where we have a whole bunch of peaks going to the left and a whole bunch of peaks going to the right in wave numbers. And each one of these peaks represents transitions between J states from the ground vibrational state to the excited vibrational state, showing that indeed these J values really do exist as a result of LS coupling, otherwise known as Russell-Saunders coupling. So in each of these spectra, what you will see are two sets of little peaks, and that has to do with the natural abundance of the chlorine isotope. So chlorine does not all exist with an atomic weight of 35. Chlorine has a 75% abundance of chlorine 35, and it has a 25% abundance of chlorine 37 with 2 additional neutrons. So every one of these peaks is doubled up, given the fact that there is a slightly heavier isotope present. So the taller peak is accounted for with a larger abundance. So the taller one's always going to be HCl with chlorine 35, and the lower peak is always going to be HCl with chlorine 37. In addition, we're going to be comparing HCl versus deuterated HCl. So hydrochloric acid and deuterated hydrochloric acid. And that will look something like this, where we have higher wave numbers, we have the double spectrum for HCl, and at lower wave numbers, we have the spectrum for deuterated hydrochloric acid. So again, down here, we have hydrochloric acid. So our H is the isotope proton, or hydrogen. And then we have chlorine, which shows up as either chlorine 35 or chlorine 37. Down here, we have deuterium, which is heavy hydrogen. So it's H2, so it has a additional neutron. So it's slightly heavier. And again, though, we have 2 isotopes for chlorine, chlorine 35 and chlorine 37. So we have 2 spectra that are separate from one another, given the heavier deuterium for deuterated hydrochloric acid. And for each one of the spectra, we double up our peaks, given the fact that we have 2 different isotopes of chlorine that we are dealing with.